All right, well, I'll get started here. Heavenly Father, we thank you for today. I thank you for these students. We thank you that you rose again. We thank you that we can serve a living God, and pray that you just be glorified in what we do, and that we would understand a little bit more about your creation today. In your name I pray, Lord Jesus. Amen. So today I need to talk about inverse functions. So before we talk about inverse functions, we first need to talk about a criteria which is necessary for a function to be invertible. All right, so before we even talk about inverse functions, I have to talk about what are called one-to-one functions. So there's various ways of describing what a one-to-one function is. Let me start actually graphically, if you will, if you don't mind. So basically, graphically, each horizontal line intersects y equals f of x at let me see here. I now want to say at intersects y equals f of x fine, I'll just say at most one point. My brain is not working. It's not giving me an alternative English sentence to this sentence, but so let me draw a picture here. So if the function is one-to-one, it might look something like this. All right, for example. So, and maybe it starts right here. All right, I don't know. If I did this right, check out these horizontal lines, right? How about this one? How many points did that horizontal line intersect the graph? 0. That's fine. That could happen. And then how about this one? 1 point, right? This one, 1 point. This one, 1 point. See, so every possible horizontal line either intersects the graph at 1 point or none. Right, so that's another English, that's a sentence you could replace my awkward at sentence with, all right? Yes, sir?
Would at more than 1 point also work?
At most 1 point is what I want, though.
Oh, I see.
I could say at, if you'd like, we could say at, here, maybe be contrary about it, at not more than 1 point.
Why don't we just say at maximum 1 point?
We could say that as well, at maximum 1 point, sure. Now, algebraically, so let's see, it's also useful to give an example like this. All right, so let me look at an example we know. We could have, for example, y equals to f of x equals to x squared minus x squared, 4 minus x squared rather. Right? So there's the graph of y equals 4 minus x squared. Is this a one-to-one function? The answer is no. Why? See, if we look at these horizontal lines, well, this one's fine, right? Up there, that's fine. That horizontal line doesn't intersect the graph at all, so that's not troubling. But what's troubling is what? If we do this one here, right? See that? We have 2 points of intersection. And if that's the case, then this function fails the horizontal line test. So that tells me f is not 1-to-1. By the way, you can also write this like this. You don't have to spell out 1-to-1. You can just write 1-1. That's fine. If you want a fancy math word for this, we like to confuse the math majors with the following word, injective. There you go. If you have like a relative who's a mathematician and you want to impress them over like, you know, over summer break or something, tell them you learned about injectivity in your college algebra class. They'll be like, what? Who's this idiot teaching you? What have they done to you? Something like that. But anyway, so do you see what I mean by fails the horizontal? So the horizontal line test, just like the vertical line test, right? If there exists a horizontal line which cuts through the graph in 2 or more points, then it fails the horizontal line test. All right? Now, this is well and good. It's easy enough to understand what we mean by one-to-one function, provided we have the graph, right? But it'd be nice to have a more algorithmic, if you will, algebraic way of characterizing it. And so here's the actual definition. Definition: f is 1-to-1 if f of a equals to f of b implies a equals b for all a comma b in the domain of f. So in other words, if we want to check algebraically if a function's 1-to-1, what we do is we, step 1, so let me just write it out here. So here's to check for 1-to-1. Number 1, set f of a equals to f of b. Number 2, show a is equal to b if possible. If it's not possible, then the function's not 1-to-1. All right? So let me look at an example. Example 1, let's look at this f of x equals to 4 minus x squared. I just looked at the graph of it here. We know this is not 1-to-1. Let's see how algebraically we can see it's not 1-to-1. Okay? It's pretty simple. We put f of a equals to f of b. So we assume f of a equals to f of b. What does that give us? For this f, how does that work out? You got 4 minus a squared, right, equals to 4 minus b squared. So we can rewrite that as what? This is the same as a squared equals to b squared, right? It's surely an accident. And if we solve this, this gives us a, or you could, this is giving us a is equal to plus or minus b. A is equal to plus or minus b. So that means that f not 1-to-1. Because we did not get just a equals b. In fact, we got 2 different things. It could be plus or minus b, right? And if you go back to the graph I had over here, right, that's very unsurprising. See that? There are 2 things that map to the same y value, and they're the negation of each other. So plus or minus, specifically, if we look at f of 1 and f of minus 1, they both map to 3, for example. So that function is not one-to-one. A one-to-one function maps each output uniquely. It never hits the same output twice. Any questions so far? No? Okay, so let's do another one here. Example 2.
I have a question.
Oh, yes.
How's your Easter break?
How's my Easter break? Pretty good.
That's good.
How's your Easter break?
Good.
Okay. Okay, good. Now that we've settled that, f of x equals to 3 plus x over, oh, I don't know, 2 minus x. Is this function one-to-one? So how do we check if this function is one-to-one? You got two choices, graphically or algebraically. Do you guys want to graph this?
No, thank you.
Not really, right? So let's do algebra. So f of a equals to f of b. We let this be true, all right? Our goal is to show that a necessary logical consequence of that equation is that a equals to b. If we've showed that, then we've showed f is one-to-one. So let's do it. I think this one's going to work out. So we've got 3 plus a over 2 minus a is equal to 3 plus b over 2 minus b. Now what? How can I reduce this equation? How about I cross multiply, right? So we have 3 plus a times 2 minus b is equal to 3 plus b times 2 minus a. Multiply it out. Let's see what happens. We've got 6 plus 2a minus 3b minus ab is equal to 6 plus 2b minus 3a minus ab. Well, this is looking pretty good because a lot of the things there are the same, right? See that? Like the 6, these 6's, they'd be canceling. Minus AB, it'd be canceling. Then what you got? We've got 2a minus 3b is equal to 2b minus 3a. Now if I add 3a to both sides and add 3b to both sides, I get 5a is equal to 5b, also known as a equals to b. So we have started with f of a equals to f of b, and we made algebra steps, right? Each of which is permissible in the context of the domain of the function. What's the domain of the function? What are the strings attached here that I don't always write down, but we should talk about them just momentarily. What can a and b both not be? What's assumed here at the outset? Right? This would matter if you're math majors. They're not 2, right? Assuming a, b not equal to 2. Don't laugh, I have found math majors in college algebra before. It has happened. They exist. What's that?
I was asking if he was a math major.
Oh, are you a math major?
No.
I checked for before, but if one of you changed to be a math major mid-semester, I might not have picked up on it. But, I mean, you'd tell me, right?
No, yeah, you did it with one on call.
Okay, yeah, that's all right. Thank you. It's good. Speed dial? Yeah. What does that even mean anymore? Anyway,
It's like when you have someone's contact.
what's dialing, right? Like,
Yeah, it's like when you have a contact page or something like that.
oh, yes. Okay, so there you have it. F of a equals f of b implies a equals b. Therefore, thus, f is 1-to-1. All right? Now, the domain matters here. Let me show you our third and final example of one-to-oneness. This one's a little bit tricky, what I'm going to do here. Let f of x equals to, let's say, x squared plus 1 for 0 less than or equal to x less than or equal to 1. So here I'm saying the domain of f is 0 to 1, okay? I'm defining it to be such, all right? Of course, if we just had the formula and we didn't say anything else, then the domain would be all real numbers, right? But suppose we're given that the domain is 1 to 1. Excuse me, is 0 to 1. Is this function 1 to 1? Let's find out. So we do what we just did. Set f of a equals to f of b, right? And that's for what? That's for a and b in the domain of f, right? So it's for a and b between 0 and 1. Okay? Now, what does that give us? That gives us a squared plus 1 equals to b squared plus 1. We subtract 1 from both sides, we get what? A squared equals to b squared. So it's kind of like my example 1, isn't it? But what's the difference? So that implies that a is equal to plus or minus b, right? So you're like, wait a minute, aren't we just back right where we were in example 1 again? This function's not 1 to 1, but why is a equal plus or minus b not a problem here? So, but we have a and b are greater than or equal to 0, so one of the solutions is extraneous, right? We find a is equal to b. It could be that they're both 0, right? Plus or minus 0, that's the one case that we get both solutions, but they're both the same. In the case a and b are both 0. Graphically, why is this okay? Like, how is this function passing the horizontal line test? Let's look at it. Maybe graphically is even easier here. What's the graph of this function look like? It's a parabola. It opens up, right? Its vertex is the y-intercept. It's 0, 1. And since it's just like this, all right? So this is y equals f of x. So does that pass the horizontal line test? It sure does, right? We eliminated the offending other half of the parabola. So this is how it, right? So there's something to think about is if you have a function which is not 1 to 1, right? What you could do in principle is you could reduce the domain, you could chop it down, make it smaller so that you remove the other piece which is, making it not 1 to 1. What this suggests is that we've given any function that's reasonably, not too wiggly, you could make the domain small enough so that the function's invertible. Now, I just said invertible. We don't know what that means yet, but yeah, go ahead.
Would you ever give us a question where we probably have to find a domain in which...
No, I don't think so. Not if I know what's good for me. I have in the past, but it doesn't go well. Frankly, that problem of restricting the domain to make the function 1 to 1, I have trouble with that question for like Calculus 1 students. So I think it's a little bit, that might be a bonus question, but it wouldn't be the heart of the test probably. Okay, so that's a 1 to 1 function. Now, why does this matter? This matters because in order to define the inverse of a function, we need the function to be 1 to 1. So let's define the inverse of a function. Definition. If f is a 1 to 1 function, then f inverse is defined as follows. All right, here we go. F inverse of f of x is equal to x for each x in the domain of f, and f of f inverse of y is equal to y for each y in range of f. Let me draw another picture to describe what's going on here. So we have x, all right? And you've got a function, right? So what happens? You feed x into the function, what comes out? Y, right? X goes into the function, y comes out of the function, right? This is what happens. Y equals f of x. What is the inverse function? Well, the inverse function, you feed y in, and what comes out? X. So it undoes whatever the function does. It's the inverse function. For this to make sense, for the inverse function to be a function, the output, what makes a function is if you give it one input, it gives you one output, right? A function is single valued. So for the inverse function to be single valued, you need the function to be 1-to-1. If it wasn't the case, when you tried to do the inverse, you get more than one thing out. If two different things map to the same y, when I try to undo it, I would have to map to both of those things coming back. So we need 1-to-1 to make sure that the inverse operation is single valued. So this is the definition. Now, so and by the way, a function which has an inverse is called invertible. So an invertible function is one which has an inverse. What? A convert. You see, convert. Are we making convertible jokes? Okay. I mean, I guess I'll allow it. So this is the definition. All right. So to check, another way to say this, let me just rewrite it again. In other words, if f is invertible, this means there is another function g such that number one, f of g of x is equal to x, and number two, g of f of x is equal to x. And to be clear, those are different x's. So like this one down here, this is for x in domain of f, and this is x in range of f. But if you want to write, you could write them both with the letter x. Just understand that those x's are coming from different places. You're like, well, why would you use the same letter for different places? Well, we do that all the time in here because we like limit ourselves to talking about functions of x alone, right? But I'm making an exception to that rule. I'm writing about a function of y over here to emphasize the distinction between where the inverse function works versus where the function works, all right? But this is a helpful way of thinking about it because now we can do some examples with this. Let's do some examples. Let's check if we've got an inverse function, all right? So like example 4, and I'll pick it from the book so it's a mystery to me as well. So let's see here. So we're in section 4.1 here. Oop, whoop, 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 nope. Yep. 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 This phone is too smart. All right, so I think this is like, it says use the definition of inverses to determine whether f and g are inverses. This is like problems 37 through 46 in section 4.1. Let's pick one to work. I'll do number 40 here. So example, where was I? Oh, 4, yeah. So here I have f of x is equal to minus 4x plus 2. G of x is equal to minus 1/4 x minus 2. The question is, are these inverses? Basically, g equals f inverse is the question. All right. When both of those conditions hold, right? We write g equals to f inverse. Okay, so let's try it out. What is f of g of x? So I like to think about that as like f of g, where g is equal to minus 1/4 x minus 2, right? So that's minus 4g plus 2. I plug in g in the place of x for the formula for f, right? This is how we compose functions. And then plugging in g, what do I get? Minus 1/4, well, minus 4 times parentheses, minus 1/4 x minus 2 plus 2. Well, that's encouraging. That's an x. And wait a minute. What? I wanted it to work. I don't think it does, though. That's plus 8 plus 2. That's x plus 10. So, nope. Not inverses. All right. Let's see here. Let's work another one here. I mean, once you find one of them doesn't work, you don't need to check the other, right? Because it has to be both of these things. So if either one of them fails, you're done.
Do you have to check them both? The first one's fine.
Yep. Yes, you do. There are situations where it works one way but not the other. So let's do another one here. Let's see here. So example 5. I sure hope this one works out. Let's do 42. That one is f of x equals to x minus 3 over x plus 4. And g of x equals to 4x plus 3 over 1 minus x. Of course, if I copy these down wrong, it could mess them up, right? So I'd be careful here. All right, so let's try it out. I sure hope these ones work. So let's calculate f of g of x, see what we get. Hey, what the? Wait. Ah. F of g of x. Did I hit somebody?
It should be funny if you hit one of them.
Oh.
How would things fun?
F of g. And so that would be, g minus 3 over g plus 4, right? Which is equal to 4x plus 3 over 1 minus x minus 3 divided by 4x plus 3 over 1 minus x plus 4. Now, fortunately, we already learned how to do this kind of algebra, right?
Mr. Cook, you have 4 weeks left of the school year. I'm ready for you to get it.
This is a hard classroom. Like, that is not an easy.
Have you ever made it?
I don't know if I've ever made it in here. No, because it's just like the tables in the way.
Here, we'll give you back one of the bad ones.
Here, try to give this
All right, fine. I'll try again.
Here, you pass it.
No, take him. Just throw it to me. Come on.
Give them more of a chance.
Yeah, throw. That'll work. I think I got carried away. All right. Don't worry. Another marker will die.
If it's too strong, you can overthrow it.
That's right. It's my ultra instinct. Let's see here. So
Batman muscles are coming out.
ultra instinct's not Batman. Come on, guys.
But the Batman muscles are coming out.
4x plus 3. So fortunately, we know how to simplify these complex rational functions, right? Yes. So I multiply by the denominator to clear the fractions. A little worried here. I hope this all works out. That's going to be what? 4x. The 3's cancel, and we're left with I think I got 5x here, yeah? You guys help me out. I think 5x is what I got there. For the top one. Would you get for the bottom? Curses. That looks to me like a 3x plus what? That looks like a 3x plus 7 to me. Yeah, go for it. Would the x cancel out? What do we mean?
To the bottom, because it's 4 minus 4x, and then you get
I'm not sure what you mean. So what I did was I multiplied the top and the bottom by 1 minus x because
Oh, I was looking at
that clears out the fractions, yeah?
so I was looking at the one in the darker black that you said the bottom.
F of g, so g minus. So apparently they're not inverses. I mean,
Can you explain where you got that 3x plus 7 from?
where did I get the 3x plus 7 from?
Yeah.
Because I have, oh,
Wouldn't that be?
thank you.
Yeah, that's what I was trying to say. The x cancels out. and
Okay,
it's 7.
that's 7. But still, Oh, wait a minute. But I made a mistake upstairs, right?
Yeah,
Woohoo! Woohoo! So this is what? 7, yeah?
7x.
All right, so there's still hope. All right, good. Whew. So it's important to be careful, otherwise you'll trick yourself into thinking they're not inverses when in fact you just didn't do algebra correctly, right?
Right.
So you're welcome.
We have no clue how often our list is that
I have some clue. Let's see here. But sorry, that was kind of unnecessary. Let's see here. But
I give you a hard enough time. I think you should be able to give me a hard time, right?
okay. Well, I mean, I'll do what I can. So g of f of x is I think of this as g of f, right? And so that would mean 4 times f plus 3 over 1 minus f. Then I plug in what f is, which is 4 times x minus 3 over x plus 4. plus 3 divided by 1 minus x minus 3 over x plus 4, parentheses are our friends. Multiply the top and the bottom by the denominator, see what we get. We get 4 times x minus 3 plus 3 times x plus 4 divided by x plus 4 minus parentheses x minus 3. And this time I'm not going to try to skip a step. I will just work those out. I get 4x minus 12 plus 3x plus 12 divided by x plus 4 minus x plus 3, also known as 7x over 7, which is equal to x. Woohoo! All right, so there you go. We have now shown that f of x and g of x as given in number 42 are in fact inverses. Are we good? Yep.
So how did you get from the 4 times x minus 3 over x plus 4?
From here to here?
Yeah.
I multiplied by x plus 4 over x plus 4. So like, just take the whole thing, right? And multiply by x plus 4 up here, and x plus 4 down here. Now I can do that because I'm just multiplying by 1. And by doing such, I clear out the denominators, and we put our fraction in the lowest forms, which in this case happens to be x. So yeah, this part of the course has a built-in review of the rational algebra stuff that you guys just saw in test 2, right? And you'll see it again on the final, of course, right? So if that stuff hasn't quite clicked for you yet, there's still time. Nope, there's just the final. So the only thing before the final is quizzes.
We have another minute.
I think there is a mission. I do think there's yeah, there's got to be homework. So, all right. So these yeah. I don't know. During the final exam period at the officially approved final exam time. So it's not like I have any choice in the matter. So it's on Liberty's website. I think I put it into the syllabus. So you should always like double check it. Okay, so May 5th. Okay, so listen, these example 4 and example 5, they're fine. They're interesting. They're important. But what's more important is to know how to actually calculate the formula for the inverse function for a given function. All right, so that's what I want to talk about next. Is okay. So this is the definition. Here's how to check if g of x works as an inverse or doesn't. But how do you actually calculate the formula for g of x if you're just given f of x? How to calculate? Find f inverse.
Mr. Cook,
What?
I can't keep a final on May 5th. I'll be celebrating Cinco de Mayo.
Oh. Well, I am teaching 2 sections of college algebra next semester, so you're a likable fellow. You're welcome to join one of those.
It's worth it.
Given it's worth it to celebrate Cinco de Mayo.
Wait, is the final in here? Just crying.
Is the final exam in here? I don't know. Is the final exam for your other courses been in the room that you've taken the course? So yes, yeah. Well, I'm sorry. Are you a freshman? If so, I'm sorry. I should not be this way. But if you're not a freshman, how dare you ask me this? Sorry. What? What color will the sky outside today be? I mean, how many questions are in the final? Is the final comprehensive? Yes, it's comprehensive. You know, I haven't. I will say this. This probably will make you happier. I've not published midterm reports in here, partly because it doesn't really mean much until you take the final exam, right? But once we, perhaps once we get the grade in for mission 3, at that point it makes sense for me to like give you some general pointers about where your current grade, you know, so I'll write up a hypothetical this is what happens if you make this grade on the final. This is what happens if you made that grade, that kind of thing. Like I'll write a, choose your own adventure story with different scenarios, and some example cases, so you can kind of gain a sense of what grade you need to make on the final in order to make whatever grade it is that you want. I mean, you want an A, right? You should want an A. Why not? Now, I would love to just tell you exactly the grade on the final that you each need to make in order to make, a different, like make the grade of C, make the grade of B, make the grade of A. And I tried to solve this problem last semester. I can't solve it.
You can look up a final exam calculator. You can put in what percent of your final grade the exam is worth, what grade you have now, and what grade you want to have.
It's much more complicated though, because I'm dropping either 1, 2, or 3 tests. Well, for you 1 or 2 tests, but not necessarily both. So it's.
Oh, you're just going to drop our lowest? I thought you
Yes. No, I will drop both of them if they're both. That's right. Don't poke the bear. So, all right. I will drop both of the tests if they're helpful.
Is that only if we score higher than that?
Well, yes, you do. You do need to give me a final exam score, which is like high enough to help. Yes, that is true.
Whichever test we score most,
I have not gotten. Listen, I have proposed in more than one faculty meeting that if I could take the tests for the students, we could improve our success rates. But for some reason, people don't let me do that. I don't know why.
I like the idea of that.
I've been extended this policy. We're having a discussion about like how to get students to read announcements more. And the suggestion that if I read the announcements for them, then we wouldn't have to worry about this. But, I have many of these thoughts. So, all right, so let me go on so I don't have to go overtime today. How to find F inverse given F is 1 to 1. Now we need a 1 to 1 function to find the inverse, right? So, number 1, let's say graphically, take basically you take y equals to f of x and plot x equals to f of y instead. Now that doesn't really mean anything, but what I specifically mean is, in particular, if AB is in the graph of y equals f of x, then BA is on graph of f inverse. Yep.
I have one more question about the final.
I feel like this is not a serious question, but go ahead.
Are we going to be able to do like some sort of final review where we like go over the concepts that will be in the final to kind of narrow down our study time a bit?
That is every day in this class.
Well, right, but that's
Every day in this class
that it would be impossible to
prepares.
actually prepare if we just could watch like 20 hours of Mr. Cook.
I mean, if you want, we could take a day and watch UHF or something. I don't know, but exactly, that's the problem.
What?
That you don't know what you don't know what UHF is. Hmm. Hmm.
Is that your YouTube channel?
No, that's not my YouTube channel. But I do think I have a review day built in. Yeah. So I mean, I think there's like a quiz and a review. It's in the syllabus, the course planner. So listen, for A comma B to be on the graph of y equals f of x, what does that mean? That means that B is equal to f of A, right? Check this out. If we take and operate on the take the inverse function of this, okay? What's that tell us? F inverse of B is equal to F inverse of f of A, right? But what's F inverse of f of A? Well, F and F inverse, they cancel each other out. That's basically the definition. So we get A, right? So this statement right here, B comma A is on the graph of F, this is interchangeable with the statement that A is equal to F inverse of B. So if I give you the graph of a function which is 1 to 1, you can create the graph of the inverse very simply by flipping coordinates. X for y, y for x. Let's look at one of those. I erased it unfortunately, but the one I had here a second ago, what is this, example 6? So example 6 is actually an extension of example 3. So we had, this was y equals f of x, right? Do you remember this, guys? So it was x squared plus 1 for, you know, I just did 0 to 1, didn't I? Yeah. So I should really just go here up to this point. 0 less than or equal to x less than or equal to 1. Okay, so let me be more explicit. What are these points? This point right here is 0, 1, right? Where does it go to? What's the top point there? When you plug in 1, you get what? 1 squared plus 1, which is 2, right? So the upper point here is 1, 2. All right. Is this function 1 to 1? Yes. It makes sense to find the inverse? Sure. What is the graph of the inverse? Very simple. All you do is flip 0, 1 to 1, 0. And you flip 1, 2 to 2, 1. Sorry, all of a sudden having a crisis of measuring. Yeah, about there. And so, you know, we could pick another point in the middle like this, you know. What would this point be here? If I put in a half, what do I get? 0.5 comma what? What's 0.5 squared? It's 0.25. 1 plus 0.25 is 1.25. So 0.5 comma 1.25 if I did it right. And so over here, you flip to 1.25 comma 0.5. So that's like here. Sorry, I'm trying to use this color code in here. So connect the dots. There you go. That's y equals to f inverse of x, graphed in red. For my y equals f of x, graphed in black. Don't be scared of this question, like on the final or on the quiz that comes up next. Like, define the graph of a function. Find the graph of the inverse function from a given graph. It's very, very simple. Just pick some points. Make sure you understand what the coordinates are of those points, and then you flip them. And that gives you corresponding points on the inverse function's graph, and then you just connect the dots, basically, all right? Now, if you do it right, there's something you can say here. Geometrically, there's a pattern here, and it should be this. The graphs should be reflections. This is the line y equals x. So the graph of the inverse function should be a reflection of the graph of the function across the line y equals x. That's the pattern that we need to see here. What I said at the top is not wrong, though. Like, really what you're doing is you're just interchanging the roles of x and y. It's the same graph, it's just run vertically instead of horizontally, or vice versa. It's the same shape, right? Just instead of going up, it goes over. So what this means is if you have a function which has like a vertical asymptote, when you look at the inverse function, that vertical asymptote is going to become a horizontal asymptote. If you have a function which has a horizontal asymptote, when you look at the inverse function, it's going to become a vertical asymptote. So it has this, there's this mirroring that happens. Those are things to look for. I goes, that's graphing. You're like, I don't like graphs, I like formulas. I hear you. So let's talk about how to find the formula of the inverse. So this is point number 2. Because a lot of times we don't want to work with a graph, we want to work with a formula, right? Do you guys like graphing? It depends on whether or not I'm talking about multiple choice. Is that fair? Multiple choice graphing is good, yes? No? Yeah? Okay. So number 2, to find formula for 1-to-1 f, to find formula for f inverse for given 1-to-1 function. All right, so step number 1, write y equals to f of x. All right, step number 1. Step number 2, solve for x. Stuff in y. All right. Step number 3. F inverse of y is equal to that stuff in y. All right. Step number 4. If desired, write f inverse of x equals stuff in x. Now, if you remember being taught this in another math class, you probably were taught a slightly different algorithm, right? Do you guys, anybody remember a different thing? A lot of times you guys are taught to switch x and y at the start of the calculation. So instead of solving for x, you solve for y. If you do that, then you find f inverse of x. The reason that I don't do that is that I think it's important actually to think about the inverse function as a function of y, and I'll show you why in an honest to goodness application here. But before I get to that application, I think it's good for us to put this into practice for a formula, right? So let's do an example here. Let's try out example. Let's try to fix example 4. See if we can find the inverse function. Yeah, that one's pretty easy. Let's see here. Example 7. Given f of x equal to minus 4x plus 2. So I guess before we get too carried away here, is this a one-to-one function? It is, right? Think about the graph of a line. It's got a y-intercept of 2. It's got a slope of minus 4. It just keeps going down. So here's a couple fun facts for you. If your function is everywhere increasing, or if your function is everywhere decreasing, those are one-to-one functions. The ones that are not one-to-ones are ones that have a turning point. They go up and then they go down. There's some kind of doubling back, something like that. Constant functions, horribly not one-to-one. Okay. All right. So let's get to work here. Step number 1. Y equals to minus 4x plus 2. Step number 2. Solve for x. Let's see here. So we've got 4x is equal to 2 minus y, right? So x equals to 1/4 of 2 minus y. There's your quote-unquote stuff in y. So step number 3, f inverse of y is 1/4 2 minus y. Which, if you want to do the somewhat distasteful but sometimes asked for last step, f inverse of x is equal to, I'm going to clean up the formula a little bit. That's actually what? That's actually, 1/2 minus 1/4 x, right? I just did that so we can compare to what was given in example 4 and see why it failed, right? Do you see it? So like the g of x we were given, it had the minus 1/4 x, that was good, right? But instead of subtracting 2, we actually needed to add a half to make it actually work as the inverse, it turns out. It's kind of amusing to me, actually, that the problem of finding the formula for the inverse is about the same difficulty as checking the function is 1-to-1. Fun thing to notice is if you can show that you have an inverse function, then that implies it's 1-to-1. So like, that's not hard to, let me just remark, I'll prove that to you. I don't prove too many things in here, but it's like a line, so. If f inverse exists, then f of a equals to f of b. What's that tell us? F inverse of f of a equals to f inverse of f of b. But what is f of f inverse? F inverse of f is just, they cancel out, right? So that gives me a equals to b, which is to say that f is 1-to-1. So if you have an inverse, it automatically follows that it's a 1-to-1 function. And when I say you have an inverse, I mean in the sense of, you know, you satisfied the f of x, g of x equations I erased up here a second ago. But all right, anyway, let me give you a real world example. Oh, I am so sorry, guys. Did I just, wait a minute. Oh, it's okay. I thought I was erasing the one I was just working on. This is like 20 minutes ago, right? So hopefully you guys are like 20 minutes behind in your note taking. Whew. All right. Let's see here. It might be instructive to graph y equals f of x and y equals f inverse of x for example 7, just to appreciate again the interplay between you know, f of x and f inverse of x. So just graphical comment. Before I go on, we just take a second here to smell the roses, so to speak. All right, so the y equals f of x has a what? A y-intercept of 2 and a slope of minus 4, right? So that's something kind of sort of like, let's see here. Very roughly, something like that. So there's y equals f of x equals 2 minus 4x, right? And what was the inverse function here? 1/2 minus 1/4 x, right? So 1/2 minus 1/4, so that's got something like here. And let's see here, the slope of minus 1/4 it's the same kind of, it's something roughly speaking like that. And if you look at this, you can see, again, that symmetry across the line y equals x. So like this half reflects over to here.